All right, this is like kind of the supplementary explanations. I had some immense confusion, kind of mixed up my right-hand rules. Aiden, another student, corrected it, and I just want to kind of provide this to you guys because I'm sure we're not alone in this confusion. But first, shout out Aiden, big help. Okay, so this is part 3. I'm not going to even worry about the numbers. I'm just going to be discussing like the right-hand rules we used here. So the first thing is, oh wait, I forgot to draw the direction this thing is moving. So is this rod that with a velocity to the left, right? And we have a magnetic field pointing into the page. So the first right-hand rule we use here is pointer finger in the direction of B. So that's going into the blackboard. Your thumb in the direction of V and your middle finger in the direction of the induced current. So this is our direction of the induced current, I induced, pointing downwards. All right. Now, fast forward to part C when we're looking for the direction of the external force such that we can maintain a constant velocity. By definition of a constant velocity, there must be no change in acceleration. Therefore, the forces need to cancel out. So the first thing to do is establish the direction of the force induced by the induced current, right? So to do that, we need to do pointer finger in the direction of the current, so pointing straight down, middle finger in the direction of the magnetic field, so that's pointing into the blackboard, and thumb will point in the direction of the force induced by the induced current. So as you can see, my thumb is pointing to the right, okay? So here's a force pointing to the right. But what we're looking for here is a force that can be added such that constant velocity is achieved and maintained. To do that, we need to have no F net equals 0. So therefore, an external force must be added in the opposite direction and also such that it's equal to F, such that, again, F net equals 0. So that's kind of where the confusion was. The right-hand rule derives the force induced by the induced current. And then in part C, we're looking for another force added to the system, in this case, an external force, that will oppose this in both magnitude and direction, such that constant velocity conditions are achieved. And the same logic can be applied to question number 4. Let me draw that out, and I will proceed with explanation. All right, so this is a similar situation and setup, but the orientation is different. We've already established why I induced points in the direction that it does. So what we do here is we have our pointer finger point in the direction of the induced current. We have our middle finger in the direction of B. This is B right here going into the page. And then our thumb points in the direction of the force caused by the induced current. So in this case, that points to the left. And again, we're looking for constant velocity conditions. Therefore, where F net equals 0. As such, an external force of equal and opposite magnitude must be added. Therefore, the force external points rightwards. So essentially, kind of the parameters of this are to have constant velocity, there needs to be no change in acceleration, which by definition means that the F net equals 0. Because there's an I induced, there's an induced force caused by that. To find the direction of that induced force, you do middle finger in the use pointer finger in the direction of the induced current, middle finger in the direction of the magnetic field, and your thumb will point the direction that force goes. These questions are asked then, what external force can be added such that constant velocity conditions are caused? That means what direction should a force, what is the direction and magnitude an external force should be added to the system such that F is canceled out? So in this case, that's going to be by F external pointing to the right. Okay, I hope this clears that up. Again, shout out Aiden, big help. I appreciate your patience, and I apologize for any confusion this may have caused. Thank you.